Okay, time to start. Very pleased to welcome all of you to today's Schrödinger lecture. You know, with the Schrödinger lecture here at the Erwin Schrödinger Institute, we try to invite people who talk about problems in physics and mathematics that are particularly interesting or that are also of particular importance for our society. And I think today's topic fulfills both criteria. It's very interesting scientifically, but it is also extremely important for our society. Actually, it's hard to think about an issue that is more important than the issue of the climate. This will certainly lead to some changes in our lives. Either we do the changes ourselves or global warming will do the changes for us. So it's certainly a topic that will stay with us for a long time. So I'm very happy to have Professor Georg Kaser here from the University of Innsbruck to speak about this topic. Georg Kaser is a climatologist and glaciologist and who has worked for his entire scientific career at the University of Innsbruck. He started there as an assistant professor, rose through the ranks, became a full professor. He served as a dean. He received many awards. He is a member of the Austrian Academy of Sciences. He serves as a vice president of the Austrian Science Fund. His scientific interests are mostly centered about mountains. I think mountains, ice, water. So actually something that, some interest that I share. We work on water and ice, but from a different perspective, more from the molecular perspective. Georg Kaser is also a fellow South Tyrolean. That's a bonus point. Very good. What I find particularly impressive is that he led many expeditions to mountain ranges all over the world, to South America, the Alps, of course, to mountains in Africa and in Asia. This actually reminds me about the time when my son was about 7 or 8 years old. And he told me, you know, when I grow up, I want to be a scientist. So I was very pleased to hear that. But then he said, yes, but I want to be a real scientist, not a scientist like you that goes to the office. I want to go explore tropical jungles and climb high mountains. So I think you are the scientist that he had in mind at that time. So it's great that Georg Kaser came to talk about climate, and I would ask you to come to the podium now to give you a presentation.
Thank you. So, Christoph Delago, thank you very, very much for the invitation, first of all of you, and for the kind introduction. I'm always surprised what people find about me when they search. Obviously, I don't know the internet or something, but it's true. And I just noted that it's probably very difficult to hide that I was first interested in mountaineering and then gradually found something which I could turn into a proper job, into science research. And that is also how I'm going to start. I went to Innsbruck, not because Innsbruck was a famous place to study glaciology, but it was not too far away from my home mountains or our home mountains. I was very much in love with the Dolomites. So I had to be there once a week or twice a week. So I couldn't go further than Innsbruck. And then, of course, I found there Institute for Meteorology and Geophysics, which was traditionally dedicated to the study of glaciers, snow and ice, actually the interface between the ice surfaces, the frozen surfaces of the, as we call it, the cryosphere and the atmosphere. And so I gradually moved into that, and that was somehow my entire lifetime. I was always working on this interface. And at a certain point, it happened. And again, it was a mountaineering experience, which somebody said, you have to go because you know these mountains. It happened that I found myself up in the tropical mountains, as here on Kilimanjaro, where we studied these vertical ice walls. Imagine this is about 6,000 meters high, or just very few meters below 6,000 meters. And it's quite of a tough work, but what a real mountaineer likes to do. And I have some young mountain guide fellows I had in my team, PhD students, but also mountain guides. And so we did some quite interesting work. And that interesting work went beyond our own little community. So that on a spring morning, or was it late morning, in 2003, I got a phone call from a person by then I did not know. He was in the finding committee for grouping together the scientists for the next IPCC assessment report. And so the co-chair of that group, of that working group 1, I'm then soon immediately coming to that, Susan Solomon, an atmospheric chemist who was very much involved in the ozone hole study, and she had somehow found my name and said, we need to have this person. Usually you get nominated by your home country, but in my case it was obviously they wanted to have me. So I first said, oh, I have to think. Of course I did not have to think, because that is the highest award you can get. You are invited to the IPCC. Now, this IPCC is something which maybe you know, maybe not. It's the Intergovernmental Panel on Climate Change, which was funded after scientists became more and more aware of the connection between CO2 concentrations in the atmosphere, the growing one, and the, so to say, the energy budget, which is expressed as a temperature, global temperature, surface temperature average. And they had failed to convince the US government. First, they were on a successful path, but then when Robert Reagan took over from Jimmy Carter, all these ideas of having kind of a US governmental panel that works on this climate change issue was dead. And so they were desperate, these colleagues, by then, and then they found finally in the World Meteorological Organization and the UNEP, which is the United Nations Environmental Program, kind of an umbrella institutions that allow it to go that bad that there was a plenary, an IPCC plenary formed, and this is until now 195 national governments plus the EU, so we always speak about 196 members. It's not scientists so far. They are all WMO members. WMO is slightly older than the UN is. It is still the biggest daughter of the UN system, and the UNEP is the youngest one and the smallest one. So they too said, we give you the umbrella, we gave you the platform. And then it started to set up the IPCC bureau, where the government still had to say who is going to lead that bureau, but they were all scientists by then in 1988, and it's still like that. And they formed 3 working groups, one on the physical science basis of climate change, one on climate change impacts, adaptation, and vulnerability. You can imagine which topics and which colleagues and which fields of science are gathering together. And one is on mitigation, how to mitigate this climate change. And I was invited first into this physical science basis as a lead author. I did the 4th assessment report by then. Then I did twice the 5th assessment report too within this group. And then I was asked to become something which is just telling you that are getting old. I became a review editor of the working group 2, certain chapters. That is when you just lead or help the lead authors to go through this rather complex workflows of writing a report. It's usually 6 years, entire cycle, 6-year cycles, 5 to 7 cycles. Now we are, within next week, we are concluding the 6th assessment report. And the core of the whole thing is a huge report, 4.7 kilograms in paperback was the last one. The pages countless. And then there is a technical summary for students, for colleagues, for whoever wants to know a little bit more. But the real part, which is part of the contract, is the so-called summary for policymakers, which is usually not much more than 20-25 pages, including figures. And that one is not just easily presented and to the governments, and you can say, now you have it. But this one is negotiated through a very, very tough approval session, word by word and line by line. If this is then approved after, it was in the pre-COVID, in the pre-internet negotiation areas bureau thing, it was 4 days, and usually it was 3 nights in a row. This is typical for UN negotiations, but for us it was very, very tough. And if that is approved, then the entire one is accepted. So they do not go back to details in principle. It's really interesting, particularly in the scientific, in the physical science basis, there is not much to change. But still, the representative of Saudi Arabia would put up his tag, his name tag, not his, but his country's name tag, and then finally, Saudi Arabia, floor is yours. And then they usually start with how beautiful the entire report is and how great the chairs are, and on and on. But my minister would not be able to understand this sentence. Don't say, you have to find another wording, or we do not like you to tell about our problems with oil, or whatever it is. They say, my minister would not understand. The next one is Angola. The next one is, I do not know. No, all the oil producing countries set up and say, my minister is also not very good. And then it starts hours and hours to change this sentence. Usually they go out and the rest continues. Anyway, I could tell 2 hours about this. And then immediately it gets published or open to public and is given to the plenary. But in order to reach that state, it has already undergone 3 review processes. And the review editors, they help the authors to go through these many thousands of review comments. Each chapter has thousands of review comments. And they have all to be answered. It's all public. All the comments by the authors, the comments, it's all public. It's a really comprehensive process. Now, just a last slide to the history of that. The IPCC is one thing, but with every negotiation on an international level, the UN sets up a framework convention in order to negotiate how the different states are implementing that, how they really follow what they have decided. And this UNFCCC, is the United Framework Convention on Climate Change, has then started in Rio de Janeiro in 1994 based on this first assessment report. Since then, they meet every year in the Conference of Parties. And the parties are the same 196 as are the members of the IPCC. But usually they don't even look to the assessment reports. Those are the ones I have been involved. So they go on and on and on, and that was rather quick to set up the Kyoto Protocol. That was not very successful. And since then they negotiate, and they finally came up with years of delay when the Kyoto Protocol was not in action anymore, or just prolonged and extended from year to year. They came finally up with the Paris Agreement, a window of opportunity, a geopolitical window of opportunity. They did it rather rough and quick and dirty. And so they have still to negotiate this Paris Agreement details. They go on and on a little bit, a step forward, 2 steps back, or 3 steps forward. Sharm el-Sheikh last autumn was not very many steps forward. Glasgow the year before was good steps forward. So that is a bit this entire frame and the setting. And I do use mostly IPCC material to give you a bit of an overview what the state of the art is. IPCC works on policy relevant science products, but is not allowed to be policy prescriptive. So the material is posed like that. Now, usually in public lectures, I use this one, not to go into videos which do not work. Then this is just to give the people an impression that we talk about a highly dynamic system, which is composed of 2 fluids, the atmosphere and the oceans, indicated here in a nice way, I think. Then there is also the biosphere, and there's the cryosphere, and the hydrosphere, and whatever, and that is highly dynamic. Now, this entire system has this global mean surface temperature of the entire system as an indicator for the content of energy. This temperature has gone up. It has gone up over the last 150 years. Compared to the last 2020 years, it had never been as high, but also compared to the last basically million years of roughly 100,000 years cycles of ice age and intermediate phases, it has never been that high as we have it now. It's all reconstructed from tree rings and from ice cores and. And we have reached already as an average between 2011 and 2020, 1.1 degrees above pre-industrial. Pre-industrial is 1850 to 1900. Before that, we have too many volcanoes involved, so it's a little bit of problematic to set it as a baseline, but this is the agreed baseline of what we call pre-industrial. So that's what we have now. And these are the drivers, well identified. Sorry for this rather small, a few seats in front. This is really IPCC material, and I fought over all the years and told them, please provide slides for presentations, but they do not. Scientists don't want, they want to have nice papers. Anyway, this is the observed warming, as I have shown you before, 1.1 degrees. From pre-industrial, and these are the aggregated drivers. This is the total human influence composed out of the well-mixed greenhouse gases and other human drivers, such as land use changes or the aerosol and so on. And those are the natural influences. You can see that there was over this period from pre-industrial until now, so to say, there was no influence from natural sources. This is volcanoes and the solar variations, and this is the internal variability, so to speak, the El Niño Enso stuff, which goes up and down. So it's all human-made, and if we then disentangle those human caused drivers, then we have, I do not go through all of them. There is carbon dioxide, the main one, the first driver, there is methane. And in many, many studies, we calculate the CO2 equivalent, which is composed of all these different impacts from different drivers. So the nitrous oxide, and you can see there is also negative impact. This is, for instance, from the nitrogen oxides, and more than anything else, it's sulfur dioxide and a few others, land use changes. So that is a bit the background, how we are able to disentangle the whole thing so far. And recently, a group of people has just composed this study. You probably don't need that, but this is a need for the public. we are heating up with a radiative forcing for the time being with about 0.8 watt per square meter. That is the period 2006-2020, and over the entire period, 71 to 20, we had about 0.5 watt per square meter. So that means, although the Earth warms up and tries to counterbalance this radiative forcing by increased radiative emission, we still are able, we speed up that much that we are able to increase even this radiative forcing. Accumulated between 1971 to 2020, actually, that is a colleague of mine had, I have not checked. He said it is about every 5 seconds a Hiroshima bomb, not in its radiation, but it's in its energy release, every 5 seconds. That's about what we have here if we integrated over the entire surface. Now, the energy gained is since then, or in this period, we have quite a bit more now, was 380 zeta joule. And that comes now 21 zeros is the zeta. And some people have not very good access to joule. They like better the kilowatt hours, which you can negotiate with your power company. So it is 106 and 80 zeros. That's quite a lot of energy. And about 90% goes into the oceans. 5% was used to melt cryosphere, 5% to heat up land, and 2 go into the atmosphere. But you can imagine that there is also these interactions like evaporation, sublimation, and then the interaction with the biosphere, the biological energy, the biochemical energy. That's all in this. They are quite interactive, also with the oceans, of course. But just to use these oceans, which of course the main change through that is the thermal expansion, but not only, come to that. But just if you imagine there were no oceans, it was just solid Earth, then we had increased our surface temperature already by 36 degrees, not 3.6, 36 degrees. Of course, we have the oceans, they hide it, they do something with it, they rise their surface, yeah, which is easier to cope than 36 degrees above pre-industrial levels. That would be something which we wouldn't be talking about anymore. And then they came to Paris. For ages before, there was always this target, don't go beyond 2 degrees Celsius above pre-industrial. But then it became more and more obvious when the temperature rose and the impacts and the effects have really been occurring already. Then in Paris, they said, no, 2 degrees is too dangerous. And I will come back to that, what the danger is. Let's try to do the 1.5. And that was an interesting situation. I went into Paris. I was attending some of these UNFCCC negotiations. I came into Paris, and that was a couple of days after the Bataclan terrorist attack. So the airport of Paris was empty, and there was only one person coming against me, and that was Kevin Riahi from YASA. And he had done already the first week, and he said, incredible, they are talking about 1.5. Watch out what they are doing. Finally, they came up and said, yeah, possibly 1.5, but never go beyond 2 degrees Celsius. And when we left Paris, we had also an order from the UNFCCC of the governments to produce a so-called special report on 1.5. And it was 90 colleagues that really sat down the next day, so to say. And in 2018, they came up with this 1.5 degree. And this is a bit the summary of what they have done. They have said or have shown this is since 1950, what the annual temperatures were up and down, and then the average or the smoothed curve went up until 2070. And then they just extrapolated and said, if we go like that, as we have come before, by 2040, we will penetrate this 1.5. And we have to avoid that because that's what we have agreed in Paris. And these are the Paris curves, so to say. This is an 83% probability if we go along this curve, and this is the 50%. And that both would not go beyond 2 degrees Celsius. So in cartoon, the Paris Agreement. But then they get further, apart from also assessing the impacts, they get further and said, what is the path to reach that? Because you cannot only say, I change the temperature, I have to do something, and that is the CO2 emissions or the greenhouse gas emissions reduction. And they came up with this number. They said until 2050, the CO2 emissions, and if you read that very carefully, it should be the CO2 equivalent emissions, they should go to net zero by 2050. That includes potential negative emissions. So far, we do not know how. We would know how to do it, but just a few bricks, but not the 40 gigatons per year or 44 gigatons per year, which we emit presently. No idea how to do that. And all these methods to reduce or to produce negative emissions, they all need a lot of energy. Where shall it come from? Oil again, coal again, I don't know. Anyway, this is a future which is beyond the next couple of years. And in order to reach that safely, we need to go through 2030 with minus 45% in compared to 2010. So I will come briefly back once again to this. Now, what happened since then, or what is the problem if we extrapolate in the future, if we do scenarios? And all these scenarios, this is now the temperature as we know it already. This is the curve we have seen now twice, 2 times actually. And now, where are we going to until 2100? And the input into the physical climate models has to come from somewhere. And that comes from the so-called shared socioeconomic pathways. And if we follow this shared socioeconomic pathway, which in other words is how we have done for the last 50 years, we would follow like that, we would end up in 2100, not just with a lot more CO2 and other greenhouse gases in the atmosphere, but also in a radiative driving of 8.5 degrees watt per square meter. So we have 0.8 now, but we would go straight into 8.5 watt per square meter. And that would just go further on. Now, we are not on that path anymore. We are basically on this one. This is what governments do for the time being. This is the shared socioeconomic pathway number 3 with 7 watt per square meter in 2100. Still going further steep through 2100. This is what they have promised to do, to reduce, to change the emissions. It's the yellow one. Still too much. We would still warm further beyond. We would reach the 2 degrees already by 2050 and go beyond and warm up more. And it's only those two that are the Paris Agreement or the Paris conform pathways. The dark blue one is the one which finally would peak in a 2 degrees Celsius or slightly below, would safely stay below 2 degrees Celsius, or the 1.5. which is the one to be favored. Okay, this is the temperature. We would then not further rise the temperature if we go along the blue lines. If we go along the red and the yellow one, we would steep go out the century with further warming. Now, there are other parameters which we can get from our climate models. And this is, for instance, the Arctic sea ice at the end of September or in September before it starts growing again. And you can see again, or yeah, we had a strong loss of Arctic sea ice already. And with the red and yellow pathways, we would soon lose the entire sea ice toward the end of the summer, which has strong implications to the ecosystems there, which has strong implications to to the resistance of the methane, frozen methane-prone coastlines, which would then be exposed to the waves and to the oceans. And there is a lot of methane. We are very concerned about that. So it is another reason why we should stay at least with a minimum of sea ice left. And there is another point which I immediately get back to. But then we have something which is not related to the energy, but just simply to the fact that if I emit more CO2 into the atmosphere, roughly about 1/3 to half goes into the oceans as a solute material. And that puts down or drives down or has already driven down the pH toward not acid yet, but still has already become very, very problematic for the coral reefs, the warm water coral reefs, which are already gone for about 90% are already gone. And if we follow the bad lines, then it's going to be very, very problematic, but it could recover if we follow the blue lines. I added this particularly for you because I usually do not take it up in a public lecture, but I thought you might be interested that this potential of taking up CO2, our emitted CO2, additionally emitted CO2, by land and oceans for the time being is 70%. So not all stays in the atmosphere. And with the different scenarios, we would end up with something which the oceans would reduce their capability, but also the land would reach a saturation. And we cannot rely on that for a long time anymore. Now, there is one variable which is really of great concern. Not that it wouldn't follow also some way how we have seen already the different pathways, but they would even go higher even if we do all the very, very ardent and very tough reduction steps to stay within 1.5 degree or 2 degrees. And this is the sea level rise. And that has two causes. One is the thermal expansion of the ocean, which is about 1/3, very roughly. That has a bit of a delay because there is not an immediate interaction with the deep oceans, but the main delay comes from ice. If you take out an ice cube from the fridge, that would not be melted immediately. It takes big one longer, small one less. And if we would stop every single molecule of emission tonight, we would still go into continuously for about 300 years, continuously rising sea level. We have that mechanism is already set on. And all our glaciers are gone in the Eastern Alps, for instance. They will be gone within a few decades because we have already changed the climate in a way that they have no stay there anymore. So if you have time next summer, go and say goodbye. They will all be gone. And the problem with all that is that we would see only, that's also with the temperature, not only with the sea level, we would only say within 2 decades whether we have reacted in one way or another. So there is a delay. But if we do the wrong things in the next couple of years, then the spread will be very, very complicated or dangerous even. But there is another point, which 1 year ago when this report, this working group 1 report was presented, they put it as a broken line. And that has not to do with melting of ice, but with the ice dynamics, the changing ice dynamics. And if they would change in Antarctica, in West Antarctica, and in Greenland, we would go much higher by 2100 than projected. For the time being, we thought, or 1 year ago, we thought we can stay within about 65 centimeters until 2100 if we are just ambitious enough and go toward these Paris agreements. Now we are rather sure that we will go to 1 meter within the next 70, 80 years because some parts have already started. And if they really start to move, and it's not just in SSP 5, we have it already here with our 1.1 degrees, that we see starting points, then the sea level would rise 1.5 meters and steeply beyond that. Now, the point is that this is the bedrock of Antarctica, right, and Greenland to the left. You see there are some mountains, there are some mountains, there are some mountains, but particularly West Antarctica is, the bedrock is underneath the sea level, is below sea level. And that makes the entire Western Antarctica particularly vulnerable. We have here this famous Thwaite Glacier is embedded here, and what is the other one? Yeah, two of the bigger glaciers, or the two biggest glaciers in West Antarctica, they have shown in front a very, very threatening behavior. Also some glaciers in front of East Antarctica here, and also some here. Mainly in Greenland, we have mainly melting problems, but here it is really the dynamics. Antarctica is too cold, there is not much melting. And this is the problem, and it's twofold. We have the ice sheet, or the ice stream coming out of the ice sheet. This is the Thwaites Glacier. The other one is the Pine Island Glacier. Those are the two famous ones, both entering the Amundsen-Bellinghausen Sea of West Antarctica, of West Antarctica, and they come out of, have all this ice flow and ice pressure, a lot of ice load that allows to fill up a bedrock that is far below the sea level. And then they come to a certain point which we call the grounding line. And beyond that, it goes usually into the ocean, or it goes into the ocean. It's already floating. Once it is there, it would not rise the temperature, the sea level anymore. But it is buttressing this ice flow. And now we see that this shelf ice, we call it, which is pinpointed on rocky islands, on old moraines, they get, through an intrusion of warmer ocean water, they get thinner and they lose the contact, particularly in the front of this Thwaites and the Pine Island Glacier, and they are disintegrating already. A couple of weeks ago, one big piece, which was broken off already 2 years ago, but was somehow stuck there, moved out to the ocean. So it does not buttress anymore. And we know from the Antarctic Peninsula that we have a 30-fold acceleration of the outflow that must not be with every of these glaciers. And it doesn't last very long, but until it gets into balance, we have much, much higher ice discharge into the ocean. And that is where this fast and very strong sea level rise would come. The other point is, with the same situation, once we disturb this pinpoint, this grounding line or grounding zone, and after that, there is not something going up the bed, then it would just drop down immediately within months and years. And maybe it finds here a next pinpoint. Maybe it finds it only here or here. And that is a very, very dangerous process, which we seem to have already started. And it is rather clear that those two glaciers, if they start going, then the entire Antarctic, West Antarctic would be lost. Not within a couple of years, not with a couple of decades. That would take hundreds of years, but or maybe even thousands of years. But once it is started, we could not stop it anymore. And that is why this rather long picture, so it ends up to unreadable small numbers here. This is what we have seen already. And if we extend it to 2300, then the blue scenarios would easily go to 2 meters, 3 meters without these dynamic effects. But if we count on this, or if we allow for these dynamic effects, if they start happening, and it seems very much that they, at least in a small scale, they have started already or are about to start, then we would rise this sea level by 2300 by 15 meters and more. And if it's here, a low likelihood, high impact storyline. So the low likelihood is more kind of a statistic likelihood and a modeling likelihood because there were not enough data. But now it's going on. It starts. So the likelihood is much more likely than it was 1 year before. Let's get away from these glaciers. It's my home field, of course, but there is also, for the first time in the 6th assessment report, people had data enough to extrapolate the extremes. And it's the hot extremes, the hot temperature extremes over land, which we show here. This is pre-industrial. It was once every 10 years. Now it is already almost 3 times. And the once in a year, in 10 years, has become hotter and longer. And so we can go to 1.5, which we think we can manage, which we are probably losing the battle within the next 2 years. Still 2 years, 2 degrees above pre-industrial, which is 5-6 times more often such events, and those that are once in a decade are much, much hotter. And we have already extreme events which are not just 2.6 degrees hotter. In Pakistan, we had one over weeks with every day 51 degrees. And soon after, was here you can also see the 50-year statistics. It's the same basically. And soon after, in Pakistan, they had a monsoon event where all this southeastern Pakistan got a monsoon, and imagine monsoon is already heaven open and just water coming down. And this past autumn, it was 7 times more than a normal monsoon, and in some regions 9 times more. 33 million people have already experienced the climate catastrophe. So it's not crisis anymore. For them, it's homeless, foodless, animalless, whatever. They are just stranded. I do not know what happens now to them. And what is biggest concern is the droughts, because they are impacting the agricultural production. Since 2018, we have observed that we are not on this dotted line. So this is what we have seen from the beginning, 2011, 2020, is already off to the left. 2020, as a single year, off to the left. Last week, the WMO has increased this number probability to 94%, that within 2026, we will reach in a single year, the 1.5. That has to do because we expect in autumn, March, April, May, a shift from a La Nina situation into an El Nino situation, which is this internal variability, which on top of everything can damp it a little bit, as it has done for the last couple of years. We had a very long extended La Nina situation, but now we enter El Nino, and we expect a boosting of the temperature increase. These are the projections. So we are not anymore on this path. Let me come back to the cryosphere, particularly to the Northern Hemisphere cryosphere. This is a picture which stems from 2013. You can just extend it. The extent of the September ice, sea ice. This is now really sea ice, which is produced on sea and which is then removed from sea, is not in contact with glaciers as the ice shelf. That was in the 1970s, and this was by 2012. So it was this reduction we have already seen in the plots. There was little reduction here around Antarctica. It was the first time that significant reduction was observed during the last couple of weeks and months. So we have seen for the first time a reduction also there. But this one has a very, very strong impact on many things we observe in the mid-latitudes. You can simply imagine that when the sun turns toward, or when the Earth turns towards the sun in the northern summer, then you have all day around sun. It's rather flat, but you still have sun. If this is 90% reflected by frozen ice or even covered with snow, then you put a lot of energy, you send a lot of energy back to the space. If that is increasingly bare, and this depending on the angle, for instance, but
what?
You have waves. Anything to me? We don't know. That appears to be rather dark. So that means that there is a lot of solar energy which is uptaken. We have seen an increased temperature rise here. Here is the scale. It's far beyond or above the global mean. That is not least through that effect. Other effects too, but not least through that effect. So it is up to 6 degrees in some parts. There is this slightly negative one, which is basically from the huge amounts of meltwater coming out of Greenland. But the rest is warming, and the Arctic is particularly strongly warming. And allow me now to use a very, very simple cartoon which comes from the Agence France-Presse. It was related to the cold waves in the US Midwest twice over the last 2 months. And the point is that the Arctic is warming stronger than the low latitudes, let's say the tropics, but also our mid latitudes. That causes a smaller difference in air pressure. This smaller difference in air pressure has an impact on the circumpolar vortex and the jet stream or the westerlies. If we have the normal strong conditions, then you have kind of a very strong vortex going around, and that does the job which it has done for ages. But if that weakens, then all that becomes more wavy, more meandering, and above that, the number of waves gets more often in a situation where this entire wave figure is not moving. It's very, very stable. And that caused not only these cold air outbreaks, which the US had to suffer for twice this winter, it's also this warm air, which is then blocked here, as when here in Canada at 50 degrees north, we had temperatures up to 49 or whatever, and forest fires. And in around the corner, around the globe, in Siberia, a lot of forest burning and permafrost melting. We have exceptional high temperatures there every summer, and of course that's going on. Now, another cartoon which is a bit disputed among the scientists, particularly with this term tipping points. These are not strictly tipping points as physicists would see it, as mathematicians would see it. It's kind of a overview of all these subsystems which may either get irreversibly changed, like Greenland, when we start with this retreat, as we have done, retreat of the sea ice, the whole area gets warmer. Greenland has started melting on the summit. Last year we had even rain, which in almost a million-year-old ice core we have never seen before. And Greenland, as we have seen, does not sit on a mountain, but in a pot. If you lower that, once you start melting, as we have started in only a few centimeters, if you lower that, you get in a lower atmosphere, and the lower atmosphere is warmer. The environment gets warmer, and if you make the air colder again, unfortunately, Greenland is too low. It would not rise anymore unless you create a new ice age. So Greenland would be lost. We have these permafrost things, we have mentioned that. We have already reconstructed a long weakening, almost 90 years weakening of the Gulf Stream, the Atlantic circulation. That has these impacts on the West Antarctica, also East Antarctica, the coral reefs, we had all that. So you see, there is a mixture of different points or critical points, which to the public we sell as tipping points. Strictly speaking, not all of them are tipping points, but it's somehow interconnected, and there is a certain fear that they may act in a compound way, cascade-wise. We start with one and then they fall like domino, let's say, whatever it is. So that is just to say that even though we now think we cannot keep the 1.5, and people start about talking, oh, then we do the 2 degrees. That's not a good idea. We should look at every single tenth of a degree, even if we go beyond 1.5. A last point, because that is politically or policymakers like that very much, there is from observations a rather linear relation between the cumulative CO2 emissions and it's, I think in that case, it's the equivalent again, but it doesn't matter, and the rising temperature. And then you can just continue to increase that by models or also with a pencil on this paper here. And then you see what the budget is to stay within SSP 1, SSP 2, 1.5 degrees, 2 degrees and beyond. And then the colleagues from working group 1 did a table. And this table says, if we would like to stay with a probability of 83%, 1.5 degrees, then by the beginning of 2020, we had 300 gigatons, the budget. Everyone is happy with the budget. We can do something. But, and this is just one and slightly different from the numbers I have given you before. This is annual rates, emission rates. And this counts with 420 gigatons with a slightly lesser probability. And this is what we have done in rates. And if we continue with that, then by 2030, the budget is gone. And we just tell people, please stop, go down, go down. If we had gone down here, we had long beyond until 2100, still a bit of a budget to be used in order to shift into new society, new technologies. But this 2030 is not a political target. It is a physical one. If we do not reach the basically net zero emissions, if we get down to 50%, then everything which we save for now, we have a little bit left to go beyond. But if we don't, then we have one day in 2030, lunchtime we have to have 50%, and by midnight we have to have 0, else 1.5 is gone. I mean, there's a bit of an uncertainty, sure, but not so much. And that caused the bunch of about 400 or 500 scientists which work in the mitigation chapter or the mitigation working group, the working group 3, to state at the very end of their report, unless there are immediate, this is 1 year ago, unless there are immediate and deep emissions reductions across all sectors, 1.5 Celsius is beyond reach. The next years between now and 2030 are decisive. We have already missed 1.5 years since then. So still the next until 2030. And I mean, it's very annoying because that was told to the policymakers since 1990. And we have set the environmental feasibility, the geophysical feasibility, technological feasibility, economic feasibility. All science has prepared. One had just to follow the paths. What we cannot change is the brains of the policymakers in the parliaments here, and also not the public behavior of this cultural, social-cultural behavior worldwide. So that is basically the fight we have to fight now this year, and that's why I go to many of these local and regional and national governments, and also talk to religious groups and whatever, whoever wants to hear, I tell. Now, just let me summarize the 2018 IPCC Special Report 1.5 pathways are not sufficient for keeping warming. That's why we have already gone. It's not linear anymore. And something which I have not very much extended, there would be all this working group 2 report to show that 1.5 degree will be tough. And we are not prepared for that. Maybe small scale groups or regions, but as a global society, we are far off being prepared to that. The risk for losing control over climate change increases with every 1/10 of a degree. And if I then take the consequences of that, then I must say we must not emit any more a single ton of CO2 unless it takes us to a net zero emission world. I could tell you how much you, but just to give you a number, if you drive 3 to 5 kilometers with a petrol car, you cause, it's easy, you can look that up in your technical sheets, you cause 1 kilogram of emission. And our models show that if we put 1 kilogram into the of CO2 into the atmosphere. Part goes into the ocean, part goes into the land. But finally, that contributes to melting is 20 kilograms of ice. So a caterpillar, 1 ton per day. 20 tons ice melted per day. So, and this must start changing our behavior. So physically, a small window for action is still exists. It's still open. Immediate and deep emission reductions are needed to just meet this window on the zero emission world, and I haven't shown that. Would be a much nicer world, much nicer one. There is in this, particularly in the working group, through a nice intercomparison or a nice summary of all studies which look into the in the UN SDGs, the Sustainable Development Goals, and there is almost in every single case there is a profit, is an advantage. And only very few cause, and it's clean water is a little bit of a, but that is something you can negotiate. Else the SDGs would just win if we go towards that. So that is my final slide. I like so much these beautiful hands and fingers of Albrecht Dürer in 1519, who they do not hold earth, but it's a pomegranate. But the way it's taken, so careful but tight, I think that is something we need to use on our home place, Earth. And this is where I get all the data from, or all the, basically all. So there is also German translations now available of the summary for policymakers. Thank you very much. If I've extended beyond time, sorry. Once I talk about glaciers, it's dangerous.